Okay, so solving exponential equations. The first thing you want to do is, can I make the bases the same? All right. And in this problem here, there's no way to write 2.4 as, say, 3 raised to the power, where we can do that with 9. So if you cannot make the bases the same, then you need to take the log of both sides. So one of the things we've learned in algebra is that you can do the same thing to both sides of an equation. Okay? So if you want to do something to one side, you have to do it to both. So the one thing we learned is that about the power rule of logarithms. And so I can take the log of both sides of an exponential equation, and I can get my x out of the exponent and move it to the front. So I have the power rule that says that now I can bring this 3x plus 1 down in front. So we have the quantity 3x plus 1 times the log of 2.4 equals the log of 9. Now at this point, there's a couple different steps you can do. You could distribute the 3x plus 1 with the log of 2.4. Okay? But for your purposes, it's probably a lot easier just to divide by log of 2.4. That way, you're working with decimals instead of the logarithms, make things a little bit easier for you. So we divide by log of 2.4 on both sides. So we get 3x plus 1 equals. Now when you do this, okay, and in the book they really suggest, and it really is a good idea, to use this number as it is, okay? In other words, when we start using the decimals, we start losing accuracy, right? Because you're always doing rounding. So if you are going to go right to decimals, until you're done, okay, you should actually use 3 or 4 decimal places. Well, what I'm going to do is I'm going to show you then how you can actually use your calculator for each of these steps so that you don't lose that anyways. Okay. All right, so I take my calculator. Log of 9 divided by the log of 2.4. All right, so we get 2.5098. Okay. So what's my next step then? Okay. So now I have this simple law or linear equation now to solve. So we subtract 1, and then we're going to divide by 3, right? Okay. So with my calculator then, I can finish that by just subtracting 1. Maybe. 1. There we go. And then divide by 3. So I'm maintaining, by doing this without rounding anywhere with my calculator, I'm maintaining the complete accuracy of my answer at least until I get to the end. And then I can round it when I'm finally done. So my answer here is going to be approximately 0.5. Okay. And then I always want to remember to check it. And so when you're checking it here then, that we're checking to see if 2.4, so bring it up here. So when I check this, I'll go 2.4 raised to the power of 3 times my answer, and do the answer second negative key, put you the answer there, plus 1. And now I'm still maintaining the complete integrity of my answer, and I should get 9. But you can do that just by checking it on your calculator too. You don't have to write out all the steps to check it. If you check it on your calculator, I'm okay with that. But those do get a little bit lengthy sometimes. Good with that? Okay, so if you can make the bases the same, it's usually pretty nice. Don't need to use a calculator necessarily for doing them. But even if you could make the bases the same, you don't necessarily have to. Okay, that's still an option for you. Okay, so there's exponential equations. Let's look at some logarithmic ones then. Oops. Okay, so number 9. Now, number 9 is actually really nice because it's one of the more basic ones. And this is very similar to when we get the same base. So the ones that I can make the base the same for exponential, if I get the bases the same, what do I say about the exponents then? Okay, they're equal. Now if you look at this, we have on both sides here log base 2, log base 2. Well, if those two parts are exactly the same, what must be true about the rest of it then? They're equal. Okay? So these two things then have to be equal to each other. So now I just need to solve the equation 7x plus 1 equals 2 minus x. So we add x to both sides. Remember, always move the smaller variable term if you have more than one, and subtract 1. So we get 8x equals 1, so x equals 1/8. Now those are a little bit more difficult to check because of the logarithm, but all I need to do is make sure that both sides are the same, right? If I put in 1/8 for x, then what's in here and what's in here are equal. Number 11. All right, so here we have log of 72 minus the log of 2x over 3 equals 0. Now, I really have two options in this case. Okay? One thing I could do, because number 9 was so nice, because I had the same logs on both sides, right? And all I had to do was set those two pieces equal to each other. Okay? So I could add the log of 2x over 3 to both sides, and I would have that same situation. Okay? Or I could use the quotient property, which says that when I'm subtracting logs of the same base, I take these two things and I do what with them? Divide them. Okay? So you have both those options. So let me just show you what it would look like with both of those options then. So whichever choice you take, so we would have the log of 72 over 2x over 3 equals 0. Or if I added the log of 2x over 3, I could have the log of 72 equals the log of 2x over 3. Now, one of those definitely looks easier than the other one. Okay? All right. The second one looks easier than the first just because I have this ugly fraction here. So if we focus over here then on the right, we could say that 72 equals 2x over 3. Okay. And then how do I get rid of 2/3? Okay. All right. Multiply by 3 over 2. Let's see, that's 36 times 3, which is 108, right? Now, I'm going to finish this other side because we're going to have problems where we need to do it that way anyways. All right? Or 14. Yeah, we're going to end up there with 14. So in a situation like this, it's definitely better to go and get them on the opposite side. So if you can get the logarithms on the opposite side, okay, with it just being log on one side and log on the other side with nothing else with them, all right, you're better off. If you can't do that, then you have to do like what we did here on the left-hand side. All right, we have to work a little bit harder with this. Okay. Now, if you do this, what am I supposed to do when I divide by a fraction? You have to multiply by the reciprocal, right? Okay. Now, we can do that, or we can do this. This is now in logarithmic form, right? Can I change this to exponential form? That was one of the first things we did with logarithms, right? We went from exponential form to logarithmic, or logarithmic to exponential. So what's the base for this logarithm? 10. So I can say that 10 raised to the power of 0 is equal to 72 over 2x over 3. Well, what's 10 to the power of 0? 1, okay? So 1 equals 72 over 2x over 3. All right, I have a couple different options. Well, here's my favorite option. Okay. I want to get this out of the denominator, so I can just multiply by what's down there. Okay. And now I have the same thing I had over there. We have 2x over 3 equals 72. And then we would just multiply by 3/2 again. So the way you do that doesn't matter, but we can see that the way on the right ends up becoming much easier than the way on the left. So if I can get them on the opposite side, so in all of those types of problems, which the only ones were like 9 and 11, okay, 13 is the same way. If I can get the logs on the opposite sides with just the logarithms, then I can solve them very easily by just setting those two parts equal to each other. To where if I have additional things like I do in numbers 14, 15, and 16, I can't do that as easily. Okay. Let's see. All right. Number 12. Log base 3 x to the 9th equals 12. Okay. Now this is really one of the easier questions because I've simplified. It's in logarithmic form right now, right? So change it to exponential. When I change it to exponential, what happens? do I get if I change it to exponential? What's the base? 3. What's the exponent? 12, right? So this is 3 to the 12th power equals x to the 9th power. That's interesting, isn't it? Okay. How many people got here and stopped? How many people didn't get even there? Okay. So how do I find x if this is x to the 9th power? Okay, square root it. Okay, kind of, except my root's not going to be 2, it's going to be 9. Okay, so you actually have two options here. Okay, remember doing fractional exponents? No, maybe that's something we're going to do later on. I don't remember. But so I can do the 9th root of both sides, and your calculator will do that. Where's that? There we go. So if you go to math and number 5, okay, I can put right, we can put whatever number we want here in the index of it. So I'm going to put a 9 there, and then 3 raised to the power of 12 here. And I get 4.33, approximately. Okay. You didn't get that? So we get approximately 4.33. And Brooke, you said you did it differently? Yeah. What'd you do? Okay. Oh, yeah. All right. You use the power rule first. Okay. So that's one way you can do it. The other way you can do it is you could use the power rule, which the power rule says that I'm going to take that 9 and move it to the front, right? So we have 9 log base 3 of x equals 12, which means then I can do what with the 9? Divide. Okay. So we divide by 9. So we get log base 3 of x equals 4/3, right? Okay. So now I've simplified that. It's in simplest logarithmic form. So now I can change it to exponential form and say x equals 3 raised to the power of 4/3. And then I could do that in my calculator. 3 to the power of 4 divided by 3. And you get the same answer. Okay? So either way, okay, you could do it either way. And this way here, the second way, by moving that 9 to the front, makes the numbers a little bit smaller then, and maybe easier to do. All right. Okay, number 14. Now in this problem, because I have that additional 2 there, I can't put them both on opposite sides. Okay? Could, but not going to in this case. Okay? And I'm actually, before we're done, I'm going to show you how you could do that. Okay? And it might make the problem easier. All right? So just follow me. First of all, what's this plus sign mean then? Okay, tells us to multiply. So we have the log of 50 times x over 2 equals 2. So the log of 25x equals 2, correct? All right. So I've simplified it to a single logarithm, and it looks like a regular logarithmic expression or equation. My base here is 10, so now I can change it to exponential and say that 10 squared equals 25x. And 100 divided by 25 is 4. Okay. So we're using all of those things that we've already developed to get to this point. All right. Now, what's that?
10 squared.
10 squared?
Oh.
Okay. So now, I'm going to do the left side just like I did the right. Do the left side again just like I had it. Log of 50 times x over 2 equals. Now, what's my base here? Base is 10, right? Okay. So, what's 10 squared? 100. So on the right-hand side, I could actually change this to the log of 100. Okay. So think about that for a second. I changed 2 to log of 100. Is that okay? Are they equal? Okay. If my base was 7, I could say that 2 equals log base 7 of 49, right? Because that equals 2 also. And it's like that problem we did yesterday in the warm-up, right? It said 2 minus the log base 11 of 121. All right, 2 minus 2 is 0. Okay. So then I could get to this point and say, oh, all right, 25x equals 100. Because now both of these things would have to be equal because I have that log base 10 on both sides. Okay. So you could do it that way. So exponential equations, okay, get same base if we can. If we can't, we take the log of both sides. Logarithmic equations, we need to simplify it so that I have a single logarithm on either both sides or just on one side. Okay? And then I can switch it to exponential form. All right. Any other questions on those? All right, so let's look at a word problem then, your favorites. Says, suppose a bacteria culture doubles in size every hour. How many hours will it take for the number of bacteria to exceed 1 million? So since it says we have just a bacterial culture, that means we have one. So my original function here then would be that let's see, use f of t is equal to 1, because that's how many I'm going to start with, times 2 raised to the power of t. Because it's doubling every hour. And they want to know how many hours will it take for the number of bacteria to exceed 1 million. So I want to know when does 2t equal, or when is 2t greater than 1 million, right? So even though I put that greater than sign there, we're basically solving this like it's an equal sign. And then we work with it from there. And there's two ways you could do this. You could do this with your calculator. I know Spencer's already over there punching in buttons. You already got the answer, right? Okay, he's already got the answer. But there's another way to do it besides that. And Spencer, what did you do? Put it in your y equals? Okay, so he went to his y equals and did it. And so let's look at that for a moment. And so y equals 2 raised to the power of x. All right, and I want to know, when is that greater than 1,000,000? So I could put 1,000,000 in here if I wanted to. And where'd you go from there?
I went to the table.
Okay, so we went to his table. All right, so second table. And, all right, so we can see 1,000,000 is 1e6, right? All right, that's scientific notation, 1 times 10 to the 6th power. So we scroll down, and okay, and we can see that it's going to be between 19 and 20, right? Okay. But that doesn't tell me the exact value, does it? Okay, that gives me a nice estimate of what it is. All right. So we could go to our window, put in here, we know that it's got to go at least to 20. All right, so let's go to 25 for my x. And my y max has got to go to over 1,000,000, right? We need to be a little higher than that. So let's go to 2,000,000. All right, so this is actually double what I need it to be. All right, so we graph it. Look at how this blue line is. It stays way down there. So we have our calculator, and we can do the intersection point then. And we get 19.93, so really close to 20. Now, that's okay, but you know what? That took me way too long. All right? I like it, but it took me way too long. This is an exponential equation, right? Can I make the bases the same? I might be able to, but I'm not sure. So if I don't know for sure, then I need to just take the log of both sides. And I'm just going to use an equal sign here for a minute. All right. So I move the t to the front, right? So it becomes t log of 2 equals 1,000,000. And so, oops, equals the log of 1,000,000, I'm sorry. And now I can just divide by the log of 2. So whenever you get an exponential equation or inequality, you can actually solve them just like you did those original ones. Can I get the base the same? If not, do the log of both sides. Or we could use your calculator. Okay? And so this will still give me the same answer. So we get 19.93. So if I do the log of 1,000,000, oops, not raise the power, divided by the log of 2. I knew it wouldn't do that. And we get the same answer. So you could do that, virtually do that either way. Complete, yes. So it says, how many hours will it take for the number of bacteria to exceed 1,000,000? So, and this is the case where it's so close to 20, probably your answer is going to be approximately, it'll take approximately 20 hours for the number of bacteria to exceed 1,000,000. Okay, we did these. And this is basically the same problems. Okay? It says use a table or graph to solve these. You don't have to. Okay? You can do it whichever way allows you to find the answer the easiest. Let's skip letter A for a second, look at letter B. When I look at this one, what's the first thing that sticks out to me for this problem here? Okay, the log base 2, okay, and the fact that when it says adding, we're going to multiply, okay? Those two things together are going to tell me right away that, hey, this is really an easy one. Because I don't need to use my calculator for that, because I can easily make this, because of the plus sign here, I can put these two together. Log base 2 of 30x, log base 2 of x plus 10, and then I can easily solve that question. Now letter A, though, just because of that greater than, becomes a little bit tougher. Plus I have this x over here, so it's 10,000x. So this is going to be a little bit tougher question because of that. So let's see what happens with they want us to use a table and graph, so let's use a table, the graph here. So we got 2 raised to the power of x plus 1 in y1 and 10,000x in y2. And so we want to find the intersection point of those two. Now this might take a little bit of work because when you say 10,000x, that thing's growing pretty fast, isn't it? Okay. And eventually 2 raised to the power of x plus 1 goes really fast. Okay. So let's see what happens if I hit zoom 6. All right, there's my first line there. There's the 2 raised to the power of x plus 1. All right, that's great. And let's see, where's 10 times? And there's 10,000x. All right, there's the advantage I have of color, right? All right, we can actually see that the line is there. So it looks like they intersect right here, doesn't it? Are they going to intersect anywhere else? Who thinks yes, they will? Okay, all right, Sam does. All right, anybody else? Okay. All right, why do you think they will?
Because you've got one that's going this way and then one that's going to eventually do that.
Okay. All right. So we need to make our window, our y max needs to be really big then, doesn't it? Okay. So let's see what happens here. Let's make our y max, let's see. If I just go to 10,000, that only goes to 1, right? Okay. So let's try 100,000 and see what happens. All right. Let's see what we get if we graph that then. Okay. All right. So we need to go extend our x, right? All right. So let's go to let's go to 30. What the heck? Let's see what happens. Ooh, it looks like they might cross, doesn't it? Looks like there's a good chance. Let's see if we can find it. All right, so now we know we're probably going to see it, right? We just got to go higher vertically. All right, so let's go to, I'm going to make this a 9. Oh, nope, it doesn't like me. So let's go to 1,000,000. See what that does for us. Oh, there it is. They do intersect another place. Good job, Sam. All right, so second trace, number 5. Click enter 3 times. Oh. And it took us back here to this one. All right. What's this number? 0. Pretty close to it. Okay. All right. We can't necessarily say 0 in that case. We would actually have to go out with all those decimal places. All right. So let's try and find the other one then. Yeah. All right. So we got to scroll over there to the other one. And we get 16.3. Now, let's look at our question here. Let me take a picture of this. So the question is, when is 2 raised to the power of x plus 1 greater than 10,000 to the power of x? And it's greater than that actually in 2 places, right? It's greater here, all right, which means all of these x values going that way. And it's also greater down here. Right? Okay. So my answer then to this problem is going to be that, and we'll use Austin's answer because it was pretty close to that anyway, right? That x is going to be less than 0 or x is greater than 16.3. Is where that's a true statement. So you might have some of these answers, you might have more than one thing then that you have to look at. And so looking at my graph then, I can see where that's going to happen.